Okay, we're now continuing this session. One thing that I did over the weekend, by the way, is I actually worked on these website, which is basically um, kind of like a nicer version of the browser that I used before. It's nicer because I'm going to be able to link all the videos, and so if anyone kind of wants to come in here and take a look at, okay, what are the HLA problems which have videos, is going to kind of go in and look for them. So, it finds the problem that we're working on, and we kind of have the raw question here to work on. We have the answer, the rational, and then we have the videos. And those actually lead to like to X. So this is where the post where I kind of put the video on. And I'm gonna I'll post a separate video on these because I definitely want to turn that into like a bigger sort of project. And but yeah, again, given the time constraints today, I'm gonna kind of go and because I want to one thing I want to, I don't know, is that gonna work? I want to try one thing, but that might be a bit distracting today. Um, but I want to see if I can just get uh, Grok voice on all the time to kind of work with me. So, hello?
Hi there. How can I assist you today?
It's a bit of as an experiment. I don't know if that's gonna work. I'm recording a video and I'm trying to solve a humanities last exam problem. Okay, so it's been going for a while already. So I want you to just listen in, and if you feel like I'm saying something where you can contribute and help me get unstuck, just kind of just speak out loud. Okay. Is that okay?
Got it. I'm all ears, ready to jump in if you get stuck or need a nudge. Just keep going with your humanities exam problem, and I'll chime in when I think I can help.
It's not a
Sounds good.
Yeah, it's not a humanities exam. It's the humanities last exam. That's the data set of the hardest problems. Blah blah blah. All this kind of stuff. It's a data set where I'm currently working on a math problem. It's a group theory problem, and I'm basically going over. You can't see the screen, but it's fine. I'm going over the different elements of the question and trying to kind of break it down. And where I left it last time was, and by the way, just interrupt me if I'm saying something where you just want to chime in or something. Um, mm, 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 mm.
All right, I'm following along. You're diving into a group theory problem from the humanities dataset. Sounds intense. I'll jump in if I spot a place to help, or if you seem stuck. Just keep breaking it down, and I'm here. What's the next bit you're tackling?
So I am right now. Let me see, because I'm actually going through the project that I have in Grok, and I think last time we were talking about group algebra, about the KG. K is a field and G is a group in group theory. So what is KG and what are the blocks of KG? So we kind of did a bit of these because we're trying to piece together what is it that we need to break. But I'm kind of a bit oh yeah. Wait a second. We were actually looking at, because I have multiple things that I could do next, to be honest, and I should actually start getting into trying to solve some of the pieces. And first, I think we want to get some hands on some tooling here. We spent the last 4 videos on understanding the definitions of, there's like a definition of a group S, of a group D, of a group G, which is then the indirect product of S over D. And then I think the gist of the whole thing is here that we have to understand. So we have to find we have to find the blocks of KG. The blocks of KG. G is the group that is defined as an indirect product between S and D. And we have a definition for both S and D. Because we need to find how many blocks does KG have, first we need to understand. First, what I want to do is I want to find a way, and maybe we can just use Python. Or we can just use Grok. We can just use Grok with code actually inside the workspace. And I wanna find a way to do to calculate compute G. To compute G, it's S indirect product over D, where the action of S on D is induced by the only possible non-trivial action of S over C3 squared, which here it says S over C3 squared equals C3. So I think that's what I want to do next. I wanna try to prove that S over C3 squared equals C3, because I mean that's what the problem states.
Okay, I'm tracking with you. You're diving into a group theory problem, trying to compute the group G, which is defined as a semidirect product of S over D, with the action of S on D induced by the non-trivial action of S on C3 squared, where S over C3 squared equals C3. That's a lot to unpack, but let's focus on that last bit you mentioned, proving that S over C3 squared equals C3. I can help with that. Since you're thinking about using Python or coding to compute G or explore this, I can suggest a way to approach it. First, let's clarify the groups involved. It sounds like C3 is the cyclic group of order 3, and C3 squared is the direct product of two copies of C3, so it's an abelian group of order 9. S is acting on C3 squared, and the quotient S over C3 squared is C3, which suggests S might be a group that, when acting, gives you a structure isomorphic to C3.
Yeah, but
To
wait,
prove
wait,
S
but
over
I did I say S is acting on C3 squared? What I said is we're defining. So we're just looking at a group that is defined as S over C3 squared. I'm not so sure if it's intentional that you said that S is acting on C3 squared. Is that another way to put it? I have a definition for S. So the definition of S is basically, I think it's a P group. That's from one of the earlier sessions, which I assume it's because it's defined as 3 and it has a an index of 1 plus 2, and then it has a sub index of with a symbol plus as well. But I don't. This is something I haven't unpacked yet. I would like to see if we can. Maybe I'll just go and switch to the chat, just so you know. I have another open window with like a chat in a dedicated project at grok.com. So I want to maybe use SymPy first to codify these, if that's fine for you. But while I do this, if you can help me understand if S over C3 squared, if what you said about the about S acting on C3 squared, is this a normal way to talk about this stuff?
Gotcha. I hear you correcting me there, and I appreciate it. You're right. You mentioned the group is defined as S over C3 squared equaling C3, and I may have jumped the gun by interpreting that as S acting on C3 squared. Let's clear that up. When you say S over C3 squared equals C3, you're likely referring to a quotient group, where C3 squared is a normal subgroup of S, and the resulting quotient, S divided by C3 squared, is isomorphic to C3, the cyclic group of order 3. That's a standard way to describe a group quotient in group theory, not necessarily an action, like a semidirect product, unless specified. Since you mentioned S is a P group, with P equals 3, and has some structure, with an index of 1 plus 2 and a plus symbol, it sounds like S might be a specific group, maybe something like the Heisenberg group, or another non-abelian group of order 27, since C3 squared has order 9, and S over C3 squared equals C3, implies S has order 9 times 3 equals 27. But we'll need to pin that down. I think your plan to use SymPy to codify this is spot on. You can define groups like C3 or C3 squared and explore their properties or quotients in SymPy. While you're setting that up in your Grok workspace, I'll keep things simple and explain that, yeah, saying S over C3 squared equals C3 is standard group theory lingo for a quotient group. If C3 squared is normal in S, the quotient S divided by C3 squared, being C3, means S has a structure where factoring out that normal subgroup of order 9 gives you a cyclic group of order 3. If you want, I can suggest some SymPy code to define C3 squared or check properties of S once you clarify its definition a bit more.
It's cool.
What do you think?
Don't. Yeah, thanks. I mean, I'll do. I think it's better if I just do that directly on the chat, in terms of the code, because it's gonna be easier for me to just look at the code and then and potentially ask in the chat to execute it. So the chat's already working on it, and what I want to understand here is the following. So the problem also talks about the only possible non-trivial action of C3 over D. Now C3, I understand what C3 is, and D is defined as C2 squared. Can you elaborate a bit more on why there's only a one possible non-trivial action between these two groups?
All right, sounds good. You're handling the coding in your Grok workspace, and I'm happy to dive into this question about why there's only one possible non-trivial action of C3 on D, where D is C2 squared. Let's break it down. C3 is the cyclic group of order 3, so it's got 3 elements, say E, A squared, where E is the identity and A has order 3. D is C2 squared, the direct product of 2 copies of the cyclic group of order 2, so it's got 4 elements, like A, E, G, G, A, G, G, where G is the generator of C2, with G squared equals E. This makes D isomorphic to the Klein 4 group, an abelian group where every non-identity element has order 2. An action of C3 on D means a group homomorphism from C3 to the automorphism group of D, aut-D, which describes how C3 permutes the elements of D while preserving its group structure. A trivial action would mean C3 maps everything in D to itself, so every element of C3 acts as the identity automorphism. A non-trivial action means at least one element of C3 induces a non-identity automorphism on D. To find out why there's only one possible non-trivial action, we need to look at aut-D.
Okay, wait, stop there, because I can't multitask, and I'm just looking at the code right now. Do you mind standing by for a second? I just wanna, I'll be talking out loud, but like, just jump in if I say something that doesn't make sense at all. But I'm looking at the code, at the generated Python code right now. So we're seeing basically using the free group library. Actually, can you expand on what is the free group library in SymPy do, and why is it called free group?
No worries. I'll stand by and jump in when needed. You're looking at the Python code in your Grok workspace, and you want to know about the free group library in SymPy and why it's called a free group. Let's dive into that. In SymPy, the free group library is part of the group theory module, which lets you work with groups like free groups, finitely presented groups, or permutation groups. A free group is a concept from group theory where you have a set of generators, say A, B, and the only relations between them are the ones required by group axioms, like having an identity, inverses, and associativity. So, in a free group, there are no extra relations, like A squared equals E, or AB equals BA,
okay,
unless you explicitly impose them.
Okay, thanks. And what does a generator mean in that context?
Cool. So you're digging into what a generator means in the context of a free group in SymPy. A generator in group theory is like a building block for the group. Specifically, in a free group, the generators are the elements you start with to create all other elements in the group through combinations, using the group operation, usually multiplication and inverses, without any restrictions or relations except those required by the group axioms. For example, if you have a free group with generators A, B, you can form elements like A, B, A inverse, B inverse, AB, BA, A squared, AB inverse, and so on, just by stringing them together. There's no rule saying A squared equals the identity or AB equals BA unless you add those rules later to create a different group. In SymPy's free group library, generators are defined as symbols, and you can use them to build words, group elements, and perform operations like multiplication or finding inverses. For instance, if you're working with a free group F with generators A and B, you might write code like free group A, B to create it, and then you can manipulate elements like AB or A inverse. It's super flexible for exploring group structures, which could help with your group theory problem if you're defining groups like S or D. Want me to suggest how you might use this?
No, it's good. I think it's pretty clear. Thanks. And I'll come back to this. I think I'm gonna stop the call now and then focus on the code, and then I'll come back to this later. Thanks.
Sounds good. I'm glad I could clarify things. Focus on that code, and I'll be here when you're ready to dive back in. Catch you later.
Okay, so why is these? Okay, as I said, I don't. The thing is, I've got like 5 more minutes. But that was a good step. So we're getting into a bit of code right now. So that code that seems to create the free group with generators X, Y, Z, and I think it's an extra special group. So I guess, can you? I want to understand how. Help me understand how you've mapped these to the specific relations list. That's what I done, because here it seems like this is what so this is what now, like Greg was telling me on the phone, right? It's like, I guess the notation just maps to it gives you information as in like what extra relations there are in this group, and that's what I hadn't seen before. So the notation 3 to the 1 plus 2 and plus refers to extra special group of order 3, and exponent 3, right? So plus indicates the type with exponent p3 as opposed to the minus type which has exponent 9. This is also known as item group over the field F3 of non-abelian group. I have to unpack these expressions. Non-abelian P groups with cyclic center ZG of order P derived group. It's too much. Okay, so the standard representation for the plus type. Okay, so that is actually just a standard presentation. So that's this plus type is a specific thing that already tells you that X, Y, Z, where, so that tells you the relations, okay, which actually matches the relations in the code. Okay. Okay, so the relationships literally come from the plus definition and the SAP index. And why do we write 1 plus 2 in the exponent instead of just 3? Because I think I explored that, but I don't remember. So that's just notation, right? So we are essentially, this is okay, and then xy, okay, equals 1, xy equals z. Okay, the relations, okay. What? Not so sure I understand these relations though. X and Z. I don't know what the notation means with the square brackets. So I have to explore that for sure. Where was I? Yeah. The structural feature of which are non-abelian group. Okay. Okay, so 1 corresponds to the exponent of the center's order. Okay, and 2k indicates the rank, dimensions over fp of the elementary abelian quotient, which is always even because of extra special group support and non-degenerate alternating bilinear form. This is too much. So the notation distinguishes extra special groups from other P groups of the same order. So P1 plus 2k, for example. Simply writing P3 for order minus 27 or for order 27 groups wouldn't specify the extra special structure among the 5 groups of order 27. 3 billion. Okay. Sorry, a one-dimensional center and a two-dimensional quotient. Okay, this is okay. Okay, let's dive into this. I'm sorry, but I need to kind of learn this because I do think that that's actually essential to the problem. Okay, so I'm gonna start the video now. As I said, it was a short one. We'll get on to another one as soon as I can. Okay, but this is where we're gonna go next. Heisenberg-like structure, one-dimensional center, and a two-dimensional quotient. What does this mean? That's what we want to do. So in this context, does it mean to have... Cool. See you around.